Yeah, so it's a really beautiful setting here. Do we need it? Yeah, so it's a really nice place here, and I'm surprised that maybe not so many people know about it. There is such a setting, and it's not easy to find a place like this, for example, in Europe, in the West in general. Anyway, so I'm going to talk about groups of symmetry. When I prepared this talk, I was trying to focus on student and non-experts, so it's going to be very general, and I focus on a couple of examples, not too much technicalities. So we can see symmetry in nature in many, many different settings. For example, if you look at animals, quite generally animals, especially like birds, mammals, reptiles, and so on, you have always, almost always, this symmetry of the faces and of the body. And for example, if you look at insects, and again, you have something similar, that there is a line of symmetry that divides the body into two. This one is working, I think. Not enough? Okay, I can use this one also. But there must be some good reason that there is such a symmetry. This must give some kind of a biological advantage to these species, that there is a symmetry. That without symmetry, maybe they would not have this advantage. Usually, if something happens in biology, there is a good reason that comes from evolution. It must give this species a kind of advantage that they would not have without this symmetry. But that's for biology. It's not the purpose of my talk. Just wanted to point out that we are always all familiar with this kind of symmetry. Sometimes this symmetry is a bit more complex, like you see in this flower. It's not just a simple line of symmetry, like a mirror that you divide into two. It's actually a bit more complicated. You have to like rotate this flower to get a symmetry, and you can rotate 3 times and come back to the original setting. So you have a more complex symmetry. And there are a lot of more other examples of flowers and plants where the symmetry is even much more complicated. You have many, many kind of rooms to get symmetry, not just like a mirror. Also, if you look at chemical and physical structures like molecules, then again it's quite common to see some kind of symmetry. For example, this molecule in the middle is the molecule of water, H2O. You have the hydrogen and then you have the oxygen, then you have this symmetric picture. There are much more complicated molecules, again, that they have very interesting symmetry. So in fact, that's where group theory plays an important role in chemistry, where they study this kind of symmetric molecular structures. And then we also learn already in primary school by looking at simple shapes and their symmetries. For example, you can see from the triangle. In fact, this thing exists in textbooks. My boy is in primary school, so I know they study this kind of thing. They ask them to find a line of symmetry of a square or of a hexagon and so on. So it's very intuitive. You don't need to know much mathematics to understand these things. And you see that when you increase the number of vertices here, then you will have more symmetry. And if you go to the extreme where you have a circle with, it looks like a polygon with infinitely many vertices, then you have infinitely many symmetries. If you just rotate the circle by any amount, you get a symmetry of the circle. And then there are some shapes where you don't see any symmetry, at least not in this picture here. But symmetry is also always not about just drawing a line, like in the example of this triangle, where you can rotate, but you can also reflect, and you can combine both of them to get all the possible symmetries. You can do something similar with any regular polygon, and that's how you get the so-called dihedral groups. So that will be the group of symmetries of some regular polygon. Anyway, these are just some very simple, intuitive examples. Then you can ask the question, so what is a symmetry? If you ask primary school student, then they will just tell you, they will just talk about these lines, where you have a picture, you draw a line, and then you have both sides are the same, you have a symmetry. But in mathematics, symmetry appears in many, many different contexts, and then it can have very different meanings, where you don't even have any shape at all. In general, you could define symmetry as, so the text here is a bit small. I hope that you can read. Can you read this text? You can define a symmetry basically of having an object, a mathematical object, this could be a structure, and an isomorphism from this object to itself. That is a symmetry. So you can define a symmetry simply as a self-isomorphism. That, of course, depends on what the object is. What is the structure, the mathematical structure of this object? And then it depends on how you define isomorphism. Even for the same object, you could have different types of isomorphisms. We will see examples. And then you have different kinds of symmetry. So overall, symmetry plays a fundamental role in mathematics and also in the history of mathematics, as we will see in some examples. One of the examples is the permutation groups, where you have a finite number of objects, and then you just permute. So you order these objects, and then you permute their places. That gives you the so-called symmetric group of n objects. This is one of the earliest examples of a group that appeared in mathematics. In fact, it played an important role in the development of group theory. So basically, group theory, there were a couple of important examples. One of them was this permutation groups. The other one was about the symmetry of this simple shape that I showed you before. So these two together then led essentially to the development of group theory. Later on, there were many more examples. But especially the permutation groups was very important because it was related to not only this just combinatorial structure, but also to a more algebraic and very important story in the development of mathematics. I will come to that in a few minutes. Let's now look at symmetry in algebra. The first one is just a very simple example where I consider the integers with the additive group structure, and then so that will be the object, and then the symmetries will be the automorphisms, which are simply the group isomorphisms from Z to Z. That will be my definition of a symmetry here. And then you can see that there are only two basically possibilities. You either send 1 to 1 or you send it to -1. So you have just two possible symmetries, and then the symmetries, not only in this example, but in general, they usually form a group. The group structure is given by composing symmetries together. So in this case, we just have the group with two elements. Let's now move to taking a k to be a field, and then kx1 to xn, the polynomial ring over this field. We say a polynomial f is symmetric if this f is not changed under any permutation of these variables x1 to xn. Then you could ask the question, if you put all the symmetric polynomials together, what do you get? Well, you get a subalgebra of this polynomial ring. And then there are some simple kind of symmetric polynomials. These are called elementary symmetric polynomials. They are given just what I have written there. For example, x1 plus up to xn. this is the degree 1 symmetric polynomial. And then you can form similar polynomials up to degree n, where you have just the product of all the variables. These are the n symmetric but elementary polynomials. And then there is an important fact which says that all the symmetric polynomials are generated by these elementary symmetric polynomials. So this is a nice algebraic result, but it is related to the next example, which is, as most of all of you know, this is one of the most exciting stories in the history of mathematics, which is Galois theory. In Galois theory, we take a polynomial f. Let's say start with one of degree 2. So I have f, a degree 2 polynomial over the real numbers. As we all learn in school, you can write down the roots of this polynomial precisely by some formulas. Of course, they may not be real numbers. They can be just complex numbers. But the point is that you can write them down precisely just using these square roots and so on. And then it took a few thousand years until people could write down similar formulas for degree 3 and degree 4 equations. And then one of the most surprising things that were proved later on by Abel and Galois was that you cannot do that for degree 5 and higher. So for polynomials of degree 5 and higher, there is no general formula for writing down the roots simply in terms of radicals. And I'm going to just give you a few sketch of the arguments here because it involves symmetry. In general, if I take K to L to be a finite field extension, for simplicity, let's just look at the case of characteristic 0, then we can define the set of symmetries here, which is the automorphism group of L over K. These are all the field isomorphisms from L to L that fix the elements of K. So this is an example of some kind of symmetry. And it has the structure of a group, and since this is a finite extension, this is a finite group. And we say that this field extension is Galois if the size of this group is exactly the dimension of L over K as a vector space. And now suppose that I pick a polynomial f with one variable over K. Suppose this is irreducible of degree n. And suppose the roots of this f, let's call them alpha 1 to alpha n. We know that these roots exist in some extension of K, similar to the complex numbers. And then let's take L to be the field generated by all these roots. Then K to L is the Galois extension. It's the Galois field extension, and a fact in Galois theory says that these roots can be expressed in terms of radicals similar to the degree 2 case. If you can do that, that implies that this group of symmetry, this automorphism group, is a solvable or soluble group. That is an algebraic, purely algebraic notion. The meaning of a group to be soluble is that you have a filtration of subgroups where each one is a normal subgroup of the next one, such that the quotients are cyclic groups. So the reason that you have this implication is that if you can write down the roots in terms of a radical, then you naturally get this filtration. Each time you add a square root or nth root of some element, you will end up with this kind of a group, and then the quotient will be cyclic. Okay, so it doesn't move. Okay, and then now the goal would be to show that if you have f of degree at least 5, then this f, the roots cannot be written down in terms of radicals, which will follow if we show that this automorphism group is not, this Galois group is not solvable. Well, suppose that we write down f in its general form. So this is not one single polynomial. It's a general polynomial where we consider the coefficients as new variables. We treat them as new variables. If you have a formula for the roots, then you must be able to write down these alpha i's in terms of these ui's, even though they are now variables, not single elements, but you should be able to write them down in terms of these new variables. Now, if we take again alpha 1 to alpha n to be the roots, then f will decompose as a product, obviously, and then we can write down the ui's, these coefficients, in terms of these elementary symmetric functions in the roots. So the function will be given by elementary symmetric functions of the roots. And then if I take E to be the field generated by all the coefficients, which are variables here, and take F to be the field generated over E by all the roots, and also I take R to be a new field, the field generated over K by a new set of variables, and S inside R to be the sub-field generated by symmetric rational functions. So they are not polynomials, but rational quotients of rational functions. Then fact in Galois theory says that this Galois group of F over E is isomorphic to the Galois group of R over S, and that in turn is isomorphic to the symmetric group of n elements. And when n is at least 5, we know that this symmetric group is not solvable, and therefore this polynomial cannot have roots written down in terms of polynomials. So as I told you, this is one of the nicest stories in the history of mathematics, is where really you could see that like modern thinking of mathematics appears. This very abstract algebraic treatment of a problem, which is people expected that you must be able to write down the roots for every degree. So it was surprising that Abel and then Galois proved that this is actually not possible. And then the proof obviously uses symmetries, and in fact is one of the first maybe examples where symmetry plays such a fundamental role. But now let's take again K to be a field and x1 to xn to be variables. This time let's consider the symmetric group or the automorphism group of the field generated by x1 to xn over K, and the question would be, what can we say about this group? This group is not finite, unlike the other case where we had finite extensions. Here, the extension from K to Kx1 to Xn is not a finite extension. It's very large. So this automorphism group is also quite large. But the question is, what can you say about this group? So the definition of this is very elementary. Even high school students could make sense of this. You just have a field and some variables. That's it, it's not a big deal. Which in a way a bit looks similar to the problems in the Galois theory, but this question is actually, well, the question itself may be old, but answers to these questions are very, very new, just in the last 10 years or so. And the techniques to answer this question uses some of the most advanced recent techniques in algebraic geometry. It's not something algebraic, not like in the Galois theory. So you have a story now 200 years after Galois. The statement, the problem itself looks kind of similar and very elementary, but the solutions are not. So for this reason, I'm going to enter algebraic geometry, and I will come back to this problem a bit later. For those of you, the students who are not familiar with algebraic geometry, for simplicity, I will work over the complex numbers, but this is not necessary. In algebraic geometry, we have two different kinds of universes. One is called the affine space. The n-dimensional affine space is denoted by an. It's simply c to the power n. So you can consider this not just an algebraic structure, but as a geometric structure, where every element will be a point with some coordinates, complex coordinates. But even more important is the n-dimensional projective space. And the projective space is defined as, this time, points, again, this will be a geometric space. Points will have n+1 coordinates for magical reasons. If you never heard of projective geometry, this will be strange. But if you work with it a bit, it becomes very natural. So the points will have n+1 coordinates, but the coordinates are not unique. They are determined up to multiplying by a non-zero scalar. And then it's not difficult to see that this Pn gives you a compactification of the affine space. Anyway, in algebraic geometry, you define algebraic varieties inside the affine space. These are called affine varieties, and they are given by a system of polynomial equations. And in the projective setting, you also define projective varieties using a system of homogeneous polynomials. So everything is defined by polynomial. Basically, algebraic geometry is about polynomials. Everything is in one way or another derived from polynomials. And almost anything you say about polynomials has something to do with algebraic geometry. I was reading about history of mathematics a few months ago, and starting from ancient times until very recent, there were two notions that seem to stand out in the history of mathematics that played a really fundamental role. One of them is polynomial. It's connected with so many of the revolutions in mathematics. One of the examples was this Galois theory, but you can go back. In fact, calculus came out of polynomials. Integration was invented basically by Archimedes, who tried to calculate area under some algebraic curves. And differentiation was invented by Fermat. Again, it has to do with trying to calculate tangent lines to algebraic curves. So calculus actually was developed in the polynomial setting first, and then people like Newton extended to a more general setting. Anyway, algebraic geometry is about polynomials. And then now let's look at some symmetry groups in algebraic geometry. If I take an algebraic variety X, then I can define two symmetry groups. One of them is the automorphism group. These are isomorphisms from X to X. If you're familiar with complex analysis, this is analog of bioholomorphic maps from some open set to another, to itself. And then we have also birational isomorphisms. These are analogs of biomeromorphic functions. So they are, strictly speaking, not even functions. They are not defined everywhere, but they have a birational inverse. So you see we have the same object, but we have two different symmetric groups. The automorphism group is naturally embedded into the birational group. If we look at some of the very simplest examples of algebraic varieties, which are just the projective spaces themselves, in the case of P1, which is just a Riemann sphere, this birational automorphism group is the same as the usual automorphism group, and this is isomorphic to PGL2, which is just the set of all the 2 by 2 invertible matrices, but up to multiplication by a non-zero scalar. For example, if you have a matrix like in the picture here, the matrix will immediately give you one of these isomorphisms. And anyway, every isomorphism will come in this way. More generally, if you go to any dimension, the automorphism group of Pn is just PGL n+1. The n by n+1 times n+1 invertible matrices, again up to this multiplication. So these are very classical groups. They were already studied a long time ago. But the birational automorphism group is much larger than this PGL n+1. As an example, if we look at the dimension 2 case, here I give you one single example of a birational automorphism. From P2 to P2, you just take each point and reverse the coordinates. That will give you a birational map. The inverse you can define, obviously. The inverse actually is itself. Phi is compose it with itself, you get the identity map. And then a classical theorem says that the birational automorphism group of P2 is generated by the automorphisms, meaning by PGL3, and this single symmetry here, this single birational map. So these things were already studied in the 19th century, and in fact, they played a very important role in the development of algebraic geometry, because the projective spaces are like the simplest kind of algebraic varieties. So especially the German and the Italian schools of algebraic geometry, they studied these things and they discovered a lot of things about geometry and algebra and so on. But some of the questions about these groups remain, they were answered much later. Okay, now some of the recent theorems about these symmetric groups, these birational automorphism groups, is these two theorems. They are actually separate theorems. The first one says that this birational automorphism group is Jordan. It satisfies the so-called Jordan property. And the definition of Jordan is given just below. It means that all the finite subgroups are basically very close to being abelian. The difference with being abelian is bounded by some constant, which does not depend on the subgroup. It just depends, in this case, just depends on the dimension. This was proved by an argument of Prohorov and Shramov, and they reduced it to some statement which I proved a few years later. The two-dimensional case was proved by Serre, and he was actually the one who posed these kind of questions. What can you say about these birational automorphism groups? And a few years later, also, some other people showed that these groups are not simple. They have non-trivial normal subgroups. So even to prove that, it is very hard. This was proved by Blanc, Lamy, and Zimmerman, the two-dimensional case by Cantat and Lamy. I forgot to put in Lamy here. So anyway, the statement is algebraic. You can just view it as a purely algebraic statement. But the proofs of this kind of statements involve a lot of algebraic geometry. And how this is related to that question in the algebra setting, I ask, let me see. Yes, you see at the bottom of this page, this birational automorphism group is in fact nothing but the automorphism group of the function field generated by a bunch of variables over C. So that last question in the algebra section, that automorphism group is precisely this birational automorphism group, which is defined in terms of geometry, but you can interpret it in a purely algebraic setting. Okay, so let's see how one can prove such a statement about this group of birational symmetries of the projective space. Yeah, maybe first I tell you a couple of things. One thing is that one of the corollaries of this statement is that you cannot embed every finite group into one of these groups. So that was one of the open questions in this area. Can you embed every finite group into this birational automorphism group of dimension 3, for example? That was not clear until these statements were proved. So that theorem implies that no, you cannot embed every finite group into a fixed one. You can embed into one of them, but you cannot fix some n and then embed every finite group. And then this algebraic statement has also a lot of applications. For example, you can use it to study topology of singularities, which doesn't seem to be related at all, but in fact, it implies nice things about structure of singularities, both geometric and topological structure of algebraic varieties. Anyway, how to prove this theorem? I will focus on the first one, which says this birational automorphism is Jordan. As you see, the proof is completely geometric. Almost very little algebra is actually involved. I mean, little group theory. Okay, let's pick a finite subgroup G of this birational automorphism group. So we should show that it has some abelian and normal subgroup of index being bounded by some constant. Well, by definition, G acts on Pn in a birational sense, not in a biregular sense. It acts birationally. But to be useful, we have to transform this into a biregular action. So we can find, by some elementary argument, we can find a smooth projective variety X, birational to Pn, where the G acts not only birationally, but biregularly. It means that G will be inside the automorphism group of X. But this X depends on this G. So if you take a different G, you maybe have to take another variety. And then if we use some of the latest developments in algebraic geometry, in birational geometry, then you can say that there is a birational transformation from X to some other algebraic variety Y, which is a normal projective variety, and it has a Fano fibration onto a base. Fano varieties are those which have positive curvature, roughly speaking. Moreover, you can do this in a way that this respects the action of the group G. So in other words, in the end, G acts on Y and also acts on T, and this map is a G map. In other words, it respects the action of G. So everything is in line with the action of G. Okay, now there are two main cases. When dimension of T is 0, this is possible and quite common to in the end get a dimension 0. In that case, this just means that you have Y, which is a Fano variety. It might have singularity, often it has singularities, but it's a manageable kind of singularity. It's not totally arbitrary. And then at this point, you apply one of my results, which say that if you put all such Fano varieties, and even much more, they all form a bounded family. That means they can be parameterized by a finite type space. You can think of, let's say, by a finite dimensional space. And once you have a family of geometric objects which are bounded, then that automatically will bound many of their invariants. In particular, we can find a fixed natural number m such that minus m times the canonical bundle will be a very ample line bundle, and that will give you an embedding of Y into the projective space of the vector space, which is a space of sections of minus mk. Now, since you have a bounded family, the dimension of this projective space will be universally bounded. And moreover, you can embed G into the automorphism group of this projective space. But we already know that the automorphism group of this projective space is PGL something for some number. But that number now is bounded. It cannot be arbitrarily large. And therefore, if we apply a classical result of Jordan himself, which basically say that this PGLN, they satisfy his Jordan property. So this reduces the statement for the birational automorphism group to the statement for the usual automorphism group, which was known much longer, maybe 100 years ago. So that is one of the cases. And then the other case is where dimension of the base is positive. That's where you have a genuine fibration. In that case, because everything respects the action of G, we will get a natural homomorphism from G into the automorphism group of T. But this may not be an embedding. And from this, you get a short exact sequence of groups, where G is our group in the middle. It goes to L. L is the image of G inside the automorphism group of T, and K will be the kernel. This K acts trivially on T, which means that this K is actually acting on the fibers of this fibration. Then, if we take a general fiber of this fibration, that general fiber itself is a Fano variety. It has also nice singularities. Then we understand the action of K K on those general fibers, we know that this K must have also property similar in the same way, the Jordan property. The K must have some abelian normal subvarieties with bounded index. Seem to be very popular today. So that takes care of K. And then on the other hand, you have L, which acts on the base. But the base is not a projective space. It could be quite different from the projective space. However, this base is so-called rationally connected. Now, there is no time to go into this thing. And the point is that we did not have to start with the projective space. We could start with any rationally connected variety and apply the same arguments. Would not make any difference, actually. And then if you have a rationally connected space, the base will automatically be rationally connected. So the induction will go through very smoothly. Anyway, by induction, again, we understand the action of L on T, we understand the action of K on the fibers, and all we need to do now is to use this short exact sequence, do some algebraic, but not too complicated arguments, and from that we can understand this finite group G. We can find a normal abelian subgroup with bounded index, and that implies that this birational automorphism group is Jordan. It satisfies Jordan's property. However, if you take other algebraic varieties, this birational automorphism group may not be Jordan. And the simplest example is to take P1 cross an elliptic curve. Then the this birational automorphism group is not Jordan anymore. That is an example due to Zarhin. But however, those two guys, Shramov and Prohorov, they proved that in fact for most other algebraic varieties, these automorphism groups, birational automorphism groups, are Jordan. The exceptions usually come from when you have some projective space cross some abelian variety. Usually that's the obstruction. Okay, so this was just one example of the role of symmetry in algebraic geometry. There are many other examples, especially when you take any finite subgroup of an automorphism group of an algebraic variety, you can form the quotient of this variety by this finite group, and then quotient varieties provide a very important class of spaces. Actually, not only in algebraic geometry. For example, in topology, you have similar things. You construct many spaces using quotient by action of some finite group. So that is the role of symmetry in general. In topology, actually, I didn't write it down because I thought I would not have enough time. But symmetry also plays a very important role in topology. Basically, if you have a topological space, take the universal cover, the relation between the universal cover and the original space is given by symmetry. It's the fundamental group which gives you all the symmetries. Symmetries there will be just homeomorphisms of the universal cover which are relatively defined over the original space. So that's another example of symmetry in mathematics. I'm sure you're familiar with many other examples, but I just wanted to tell you that even some simple looking statements could be very, very hard to prove about symmetry of some objects. Okay, I will end my talk here. Yeah, so for most other ones, for example, those which are not uniruled, their birational automorphism group is Jordan. This is also proved already. But as I said, if you take P1 cross an abelian variety, then you don't have this. And another nice property is that for varieties of general type, these groups are all finite. Yeah. They are usually discrete, except, I mean, if you take a genuine Calabi-Yau, not like a billion varieties, they are discrete and their structure is quite complicated. So its connection with the geometry of the Calabi-Yau is the so-called cone conjecture, which in fact originates in mirror symmetry. But it's a very difficult problem and still widely unknown. Any algebraic variety. Okay. I'm not sure if I understand the question. You mean whether for any algebraic variety this birational automorphism group is the automorphism group of some algebra? Yes, I mean, because when you take the any algebraic variety and you look at all the birational maps, then this will give you automorphisms of the function field. So it's exactly the same statement for the function field of the variety defined over the ground field. So yes, for every algebraic variety, it just corresponds to some field extension. Sometimes, yes. For example, they, at least in the case of the automorphism group, they act, usually how you study them, they act on some spaces. Usually that means you take some line bundle, then they act on the space of sections of this line bundle. That will give you a representation. So that's one of the standard ways. If you have just a birational automorphism group, then usually you, for the whole space, I think will be difficult. But if you take a finite subgroup, you regularize it, and then that will give you some representation. That I don't know. I think that would be hard probably to show that every group which is Jordan comes from some algebraic variety. My expectation would be no, but yes, yeah, of course. But you could also have strange groups coming from outside. I don't know. Yeah, it would be nice to give some examples or to show that they're actually all coming from varieties. I don't really know. Could be. I don't know exactly what to expect. Yeah. Of the manifold. Yes, it's a nice question, but I don't know the answer. There was some question? Actually, in characteristic P, these groups are not Jordan. That's already known. But you can basically take any field of characteristic 0. They don't have to be algebraically closed. Then you have the same statements. It is not affected because when you blow up, it's a birational operation, so the group will not change. It's the same. If you take two varieties in the same birational class, their automorphism group can change, but their birational automorphism group will be the same. Well, the statement applies to all finals, to any rationally connected, not only final. It's the same. Yeah, so those which are not Jordan, they are actually exceptions. They usually are birational to product of projective spaces with abelian varieties. That's usually where you have abstractions.
Other questions from Zoom? Okay, if not, let's